Hi, I'm Sagar Karandikar. I'm a first-year PhD student at Berkeley, but I've been working on adding support for the RISC-V instruction set architecture to QEMU. So quick outline. I'll talk about why RISC-V was created, just generally the benefits of having an open ISA. Hopefully that won't be too much of a tough sell here. I'll talk a little bit about the ISA itself, a little bit about the architectural features of the ISA, why it's designed the way it is. I'll talk a little bit about virtualization support in kind of more classical virtualization terms. And then also we kind of have a gap in the hypervisor spec that I'll ask for your help with. Then I'll talk about the actual QEMU target support for RISC-V that's been developed. And then some more information about kind of the work in progress, what we need to do to upstream, and then some future plans. OK, so first thing, you could argue that ISAs don't really matter, right? So if you look at a full computer system, there are a lot of different things that contribute to the performance and energy characteristics of some application running on a machine, right? So from the beginning, you design some algorithm, right? It has some runtime complexity that you have to worry about. Then you actually write the code. Your implementation quality matters a lot. Then you have to go through a compiler, your OS, and your runtime, whether you're using a managed language or something else. And then in here is the ISA. It's one particular component of this. But even after the ISA, there are a ton of things that matter. So how you design your microarchitecture, what kind of trade-offs you make when you're actually designing your core, how large your caches are, all of that stuff. And then even once you do the architecture work, then you actually have to go down and fab a chip, right? So there's lots of stuff there that impacts how your actual system performs, right? So from this perspective, it looks like ISAs don't really matter, right? It's just one small sliver of this giant stack. But you can also say, you can also argue that your instruction set matters a lot, right? And if you think about the answers to some of these questions, well, why can't Intel sell mobile chips? It's because most existing mobile devices are based on the ARM ISA. Why can't ARM sell servers? Well, most existing servers are built on the AMD 64 ISA, and most of those machines are supplied by Intel. And how can IBM still sell mainframes, with the oldest being IBM 360-based ones with kind of an ISA that has survived over 50 years? Right? And the answer for a lot of this is that software development cost is really high. Right? To build software that runs well on these different machine types takes a lot of effort. So given this, you can argue that your ISA is, in fact, the most important interface in a computer system. Right? This is ultimately where you go from just building a piece of fixed function hardware to something that's really programmable. And if we look even further to like modern systems, there's more than just one ISA on something like a system on chip. Right? So there's, for example, an NVIDIA Tegra here. There are tons and tons of different types of processors on board. So of course, there's the application processor, generally ARM. But then there's tons of other kind of accelerator class processors. So there's graphics processors, image processors, all kinds of DSPs, security processors, power management units that are sometimes just small regular cores. And then the list goes on and on. Right? But generally speaking, the application processor ISA is much too large to be used well for these small accelerators. And in fact, a lot of times when you're building a system on chip, you're buying IP from a variety of vendors. And each one of these pieces of IP will have their own proprietary ISA frequently. And sometimes you want to develop your own cores. Right? If you're building one of these accelerators or even building your own CPU, people will implement their own ISA, right? Because they need some constrained feature set or they need to add things that don't exist. And as a result, they all have to keep bringing up new sets of compilers, runtimes, operating systems to go on top of this. So some SoCs today have over a dozen ISAs on board. And like I said, every single one has to have its own unique software stack. So this is a ton of engineering effort to kind of do things that have already been done over and over. So a couple of questions then. Do we need all these different ISAs? Do they have to be proprietary? And the most important one, what if there were one free and open ISA that you could use just for everything? So I'll argue that ISAs should be free and open, not bound by kind of legal constraints. Right? So lots of ISAs are proprietary for a variety of reasons, but largely these reasons are historical or business reasons. Right? So there's not really a good technical reason for why we don't have an open ISA so far. So it's not an error of omission. It's not like someone working at one of these big companies woke up one day and goes, oh man, I forgot to open source our ISA, right? It's not because companies do most of the software development. As we see in settings like these, there are lots and lots of contributors to system software that runs on these machines. Companies also don't exclusively have the experience to design a competent ISA. There are lots and lots of textbooks about how different ISAs behave, what kinds of ISA features are good and bad in with modern implementation techniques, and so on. The most popular ISAs are definitely not the most wonderful ISAs. There are all kinds of complications that have built up over time with legacy. And neither can only companies verify ISA compatibility, right? You can have just as easily some type of foundation that creates compatibility suites to make sure that some processor implemented by someone who's unknown kind of matches a spec, right? Or as close to matching a spec as we can determine. And then lastly, proprietary ISAs are not guaranteed to last. So there have been lots of big companies having their own ISAs in the past. Those companies are gone. Those ISAs are unsupported. So there's no guarantee that just because there's a large corporation backing something like an ISA that it's going to last forever. So what are the benefits of having a free and open ISA? Well, some of these are kind of obvious. So greater innovation via free market competition. So because the ISA is standardized and anybody is allowed to implement cores that match that ISA, you can have lots of different cores, both closed source and open source, and you get competition that way. You can have shared open core designs. So I'd say large quantity of systems that get built, the performance of the actual core on board is not the differentiator of the product, right? So in that case, really all the designer needs is just some core that works and executes instructions fairly well. And so having these shared open designs is really good. Processors need to become more affordable for more and more types of devices. So there are devices like IoT devices where you really want cheap things. So if you can get something free and open source and it doesn't need to be the fastest CPU out there, this is another good way to do it. And software stacks can survive a long time when kind of the people working on them are distributed, not related to just one company. And you can upgrade the software. You need to be able to upgrade the software in systems that, for example, have been embedded in concrete, right, for IoT type devices. So you need long-term support to make these kinds of things work. And then lastly, a big thing that has developed in the systems research community is that you can do really good practical research because of all the open source system software that's available there. So in architecture, kind of the field is more narrow in this regard. So we want to make architecture research much more real by having fully open hardware stacks and then having all of the software pre-built on top. So someone who's doing research can modify real cores that are actually used in real devices if they're open source, and they get all the software effort that's been put into porting things like GCC and all of that stuff for free. So where did RISC-V come from? So back in 2010, after lots and lots of years using various ISAs for projects, computer architecture researchers at Berkeley took a look at what kinds of ISAs they wanted to use for their next sets of projects. A couple of obvious choices here. So there's x86 and ARM. If you think about implementing with x86, well, first off, it's too complicated. So it'll probably take a couple of PhDs to get a processor that works in the first place. And then you get sued, right? So that's no good. And just as a sample of this complexity, you can look at something like the AAA instruction in Intel x86. This does something really complicated for BCD math, but it's a single byte instruction, and it's not really that important in modern machines, but it's something you have to implement if you want an x86 compatible processor. We can say the same thing about ARM when you're trying to implement kind of a nice simple processor. It's pretty complicated, and then in the end, you either have to pay a lot of money or you get sued. So same problem in the end. And so at Berkeley, we started a 3-month project back in the summer of 2010 to develop our own clean slate ISA. So the principal designers are listed here. And a lot of them are now involved in a startup that's building cores based on RISC-V. Some more background. So I said 3-month project. It's in quotes for a reason. If you jump to 4 years later, in May 2014, we released the base frozen user spec. And on the way, we had lots of chip tapeouts that I'll talk about in a couple of slides, and lots of research publications. So we're really dogfooding this and using RISC-V to actually develop systems that we use for research. The name RISC-V was chosen to represent the kind of history of RISC design at Berkeley. So there were the original RISC publications back in 1981, and a variety of revisions of that and further developments all the way to Spur. And a lot of these influenced architectures like Spark, for example. So RISC-V is kind of the fifth version of RISC coming out of Berkeley. And then if you jump forward to August 2014, articles of incorporation were filed to create a nonprofit RISC-V Foundation to govern the ISA and kind of make sure it develops without a particular special interest like Berkeley controlling the whole thing. So what is RISC-V not? So it's important to distinguish the fact that RISC-V is not an open source processor. So it's just an ISA specification, not any set of cores. So at Berkeley, we do develop open source cores that implement the RISC-V ISA, but the ISA stands alone. It's its own entity, and it's open source because anybody is allowed to implement things that conform to the ISA, and you won't get sued for implementing a RISC-V core, for example. And the reason for doing this way is that most of the cost of chip design is in the software. So bringing up the huge software stacks that run on a particular chip in advance, conforming to one standard ISA means you can reuse this across a bunch of different chip designs. And the goal of the foundation essentially is to kind of make sure the ISA grows well, has feedback from the community, and we want to encourage both open source and proprietary implementations of the RISC-V specification. So it's not designed so that everything has to be open source. So this way, companies can use it to kind of build their own closed source cores with special sauce on top, so that they don't have to open source that kind of stuff if they don't want to. A brief history of the cores at Berkeley. So these are all cores that have been designed at Berkeley, fabbed, and we actually have the chips back. They run things like Linux on top. They're fairly performant, especially given that they're written by a couple of grad students. And we fab them in pretty modern processes, and this timeline keeps going. We keep sending out chips to fab. We can keep getting them back, and they get better and better. So we have actual implementations of RISC-V out there. And there are other companies and startups working on building them too. Just quickly to show you the backing behind RISC-V now, there are a lot of companies that have joined into the RISC-V Foundation. So there's a bunch of industrial sponsors who have paid money to participate in the RISC-V standardization processes and kind of directing how RISC-V works into the future. Another slide full of more companies that are also contributing. So I'll talk quickly about the actual ISA itself. So there are, at the base, 3 different address space variants defined. So there's 32-bit for embedded type systems, 64-bit, which is your current standard server class, desktop class machine. And then there's also a 128-bit address space provisioned in the ISA for kind of future use and larger data center global address space type environments. The base ISA consists of only about less than 50 integer instructions, but this is enough to support compiler, linker, your operating system minus privilege instructions. And then the design of RISC-V makes it really easy to add extensions on top. So the idea is that unlike other ISAs or previous ISAs, things that get bolted on later get bolted on into specific areas that are predefined in the specification, so that it's very easy to, in the future, have a piece of software that can tell exactly what version of the ISA the processor implements. And all of that functionality is baked into the ISA at the beginning. So all of that feature detection, all of that stuff is pre-planned out. And so more standard extensions provide things for the general purpose ISA, like floating point and atomics and stuff like that. So if you look at ISA level metrics, so they're very comparable to other RISCs. And in fact, there are some recent tech reports out of Berkeley that do things like compare it to even more ISAs, x86, ARM, talk about cool things like macro-op fusion and breaking things into micro-ops and so on. So like I said earlier, the ISA is really designed for extension and customization. So the idea is that we know that people are going to want to add things to the ISA in the future, both as standard extensions and non-standard extensions. So the ISA is designed to be able to adapt very well to to future extension without breaking everything and making things like virtualization really hard. And like I said earlier, we've had 12 64-bit silicon prototypes. So they're actually real implementations of RISC-V that we have. We run Linux on, stuff like that. Some more stuff about the actual ISA. So there are a couple of instruction formats for the base ISA. All of the instructions in the base ISA are 32-bit fixed width, naturally aligned, relatively simple. There's the usual 31 integer registers plus a hardwired 0x0 register. A neat thing is that RD, RS1, and RS2 are all in a fixed location, and there are no implicit registers, like, for example, in that AAA instruction that uses some specific set of registers that's not actually noted in the instruction itself. So here, you know, like RD is specified. You know what when you look at the instruction itself, what registers it's using, and there's no magic happening behind the scenes. Another feature is that the immediate field is always sign extended. So if you look at something like MIPS, there are a bunch of rules about how when things get sign extended, zero extended. None of that stuff happening here. It's easy to remember. Everything gets sign extended. Floating point, adding the floating point extension adds floating point registers, floating point control status registers, and also some extra instruction formats, for example, for fuse, multiply, add, where you need additional registers specified in your instruction. And the base ISA is designed to very neatly allow things like position-independent code and dynamic linking without kind of weird hacks. OK, so what is RV64G? So I'm pointing out RV64G because this is the general purpose ISA, and this is what QEMU implements right now in our version of QEMU. So G stands for, G is general purpose, but it includes the standard extensions I, M, A, F, D. So I is the base integer ISA that I was talking about on the previous couple of slides. Then you have a bunch of other standard things that you might want in kind of regular desktop class or server class system. So you have standard integer multiply and divide extension, standard atomics, and then 32-bit and 64-bit floating point extensions. And like I said, this is the standard general purpose version of the ISA, and this is what QEMU implements minus the privilege part, which I'll talk about in a second. So far, what I showed you is stuff that's standardized. So the user level ISA is frozen, standardized, and not subject to change. So on the other hand, we have our privilege specification, which is still under development. So I'll tell you how it is kind of as it stands, but some of this stuff is subject to change in the future. So right now, there are 4 privilege modes. So you have user, supervisor, hypervisor, and machine mode. Machine mode is required in every single system. But a common case is to do something like provide machine mode, supervisor mode, and user mode for running things like Unix-like operating systems. So this is what QEMU does right now. Then you have to worry about kind of your memory translation type stuff. So the virtual memory architecture is basically designed to support standard Unix-like operating systems. So there's nothing crazy going on here. For example, the SV39 spec that's used in RV64, which is 64-bit RISC-V, you get the regular stuff. So you get demand page virtual address space. In this case, SV39 means it's a 39-bit virtual address space, 3-level page table, and you can have pages of various size, with the standard being 4 KB. And there are a variety of different address space sizes depending on what your system needs, and these are all standardized in the specification. So since this is particularly interesting here, I'll talk very briefly about virtualization kind of in the classic sense. So virtualization is something that is sort of baked into the ISA from the beginning. So we're trying to pay attention and make sure that it's easy to virtualize our system. So even if you're just using user, supervisor, and machine modes, RISC-V is designed to be virtualizable in that sense. So this is a quote directly from the manual to show that designers are paying attention. Right? The privilege architecture is designed to simplify the use of classic virtualization techniques, where the guest OS is run at user level, and as the few privilege instructions can be easily detected and trapped. Right? So I'll talk briefly about avoiding some classical virtualization pitfalls in the context of the original VMware paper that described some of the hardships they had in adding virtualization on an operating system running on top of x86. So one of these things was handling sensitive but unprivileged instructions. So if you look at this paper, when they were building VMware for x86, they have this quote: Table 2 lists the 19 instructions of the x86 architecture that unfortunately violated Popek and Goldberg's rule. and hence made the x86 non-virtualizable, at least without kind of hacking things. So in RISC-V, there's no such hidden privileged state reads or writes going on. So there's a small set of privileged instructions that can modify this space of privileged state, which we call control status registers. And this is kind of its own address space of specific registers. And encoded in the register numbers themselves is information about permissions, like what kind of mode you have to be in to read or write this particular register. And as a result, it's very easy to tell, based on what mode you're in, what kind of modifications are allowed. So as a result, it's very easy to do the regular run things natively and do trap and emulate for privileged instructions when you encounter them when you're trying to virtualize. So RISC-V basically doesn't have this problem of hidden privileged state reads and writes. Next up is dealing with changes in virtual machine memory, so kind of management stuff. So for the original VMware, this is quote, privileged hardware registers contain the address of segment descriptor tables and page tables, but these things get modified by regular loads and stores that obviously don't trap, and so you can't tell this is going on. So in RISC-V, you still use regular loads and stores to modify memory management state, but by spec, you're required to have this sfence VM instruction after your loads and stores that modify like a page table. So this is a privilege instruction. As a result, if you're running this in user mode, it'll trap and you'll know, and you can do your usual emulation to fix things up in your monitor. Last up is virtualizing segmentation. This is kind of the easiest fix. So I had to paraphrase this paragraph here because it was too complicated to put on the slide. But essentially, there's a variety of hidden state, a large amount of hidden state that gets modified in x86 when you do things like mess with segment descriptor tables and registers. In RISC-V, the fix is easy. There's no x86 style segmentation, so there's none of this segmentation on top of paging. So if you want this kind of limited base and bounds mode, this is available in machine mode and stuff like that. And you get a couple of segments. You get this kind of neat, easy protection. But we expect that regular systems will use paging instead. And so as a result, we don't have this problem with hidden state getting modified with dealing with segments and stuff like that. So all of our memory management happens through pages, and it's nice and easy to detect what's going on. Another thing about the ISA is that the sort of logical breakdown of software inside the ISA is designed to make it very easy to virtualize. So this idea of having these like clean abstractions inside of software that's running on the ISA is supposed to make it very easy to kind of swap out any of these base components and virtualize. So the idea is that we want to provide very clean, well-defined layers inside the software stack itself. So something that's already common, your applications communicate with the OS via some application binary interface, so that's no different. But what we want to do in RISC-V is extend this all the way down the stack. So for example, your OS now is going to communicate via some supervisor binary interface to a supervisor execution environment that's provided by some more privileged software. And you can extend this down to hypervisors and so on. So the idea is that all levels of the ISA are designed in advance to support virtualization. But of course, we need your help for this. So the hypervisor specification right now is an empty chapter in the privilege specification. So it's something that's kind of being worked on. Right now, what you can do with the current privilege design is have this M-mode monitor that provides very simple physical resource partitioning and can act as a very simple hypervisor. Of course, we want to have more full-featured hypervisors on top. So there will be a hypervisor extension specification. Like I said, it's an empty slot in the privilege architecture design right now. If you're interested in getting involved in this, I would encourage you to join the ISA dev mailing list. The idea is that someone will write up kind of a first draft of this, and then drafts will make the rounds on the ISA dev mailing list. We take feedback, things get fixed up, and it'll make its way through different committees in the foundation and eventually get approved after we kind of know it works well. Last kind of specific thing about RISC-V, I'll talk about the RISC-V ecosystem itself. So we have a bunch of software built up. So your regular compilers and stuff, we have GCC, we have glibc, GDB available, LLVM and Clang are there too. We have a Linux port that's being improved on pretty rapidly, but it boots up. You can kind of work with it, type in commands at command line, run a shell, whatever. We have Yocto, which generates embedded distributions for kind of small embedded systems. We also have a verification suite of standard tests that we hope will be expanded onto. I'll quickly go through the hardware we have. So we have some FPGA infrastructure if you want to buy an FPGA and put your own RISC-V cores on there. I'll talk about Chisel in a couple of slides. So I'll skip that for now. In terms of software implementations, we have Spec, which is our golden standard ISA simulator. So the thing about Spec and the reason we call it golden standard is that Spec is written by the same people that write the specs for the ISA. And so as a result, you can run against it and kind of say that if Spec does something, you're allowed to do it. And that's how we do some testing, and I'll talk about that towards the end. Then we have Angel, JavaScript ISA simulator. If you're interested, you can go to riscv.org/angel and watch it boot Linux in a browser. Then QEMU, obviously, which I'll talk about in a second. And then we have a bunch of hardware implementations. So we have Rocket Chip, or the Rocket Core, which is a RV64G single-issue in-order pipeline. We have the SODOR processors, which are educational processors. And then we also have Boom, which is our kind of large-scale out-of-order processor. And we've shown in the past comparable metrics to a variety of ARM cores. OK, so why this talk is here, right? I'll talk a little bit about RISC-V target support for QEMU. So right now, this is maintained on the RISC-V organization on GitHub. We're obviously hoping to upstream, and I'll talk about what we want to do for upstreaming in a couple of slides. But so it's maintained here. We have QEMU full system emulation, no Linux user mode right now. On modern x86, the kind of funny thing is that QEMU is the fastest RISC-V implementation. So this will probably be eclipsed in a year or two as real cores start to come out. But right now, we're the fastest. And a cool thing is that this has been a really big help in developing software for RISC-V, especially when we don't have really powerful production-grade cores to develop software on. So real quick, I got to show the obligatory slide that shows it works. So on the left-hand side is Spec booting Linux. On the right-hand side, QEMU already finished. And so you'll see Spec finish up, and you can run commands and do whatever with it. So that's to show it works. I'll talk briefly about the timeline of RISC-V first. A lot of things happened first on QEMU because we started QEMU development back when I was an undergrad in 2014. It was like May 2014 or something, and I started working on QEMU. About a month later, we had the first Linux boot on QEMU, and it was immediately the fastest RISC-V implementation. Then it was also the first RISC-V implementation that had TCP/IP networking. So we had VirtIO networking devices. You could SSH into this. You could interact with a GUI on top of Linux running through VNC and stuff like that. Then it was also part of the first Python bring-up. So the first time that real software and Python was run on top of RISC-V happened on QEMU. Also, the first Java bring-up happened on QEMU. And something I think is particularly cool is that the first RISC-V core built on a RISC-V system happened in QEMU. So I'll talk briefly about how we build chips at Berkeley. So we have our own DSL for developing chips called Chisel. So the idea, it's not like high-level synthesis. It's not like you write a C program and it converts it into a circuit. Chisel is a way to make it easier to develop hardware kind of in a similar fashion to what you would do in Verilog. So you still are describing hardware. But the idea is that you apply good software engineering techniques and good programming language features to designing hardware. So Chisel is a DSL that's embedded in Scala for generating hardware. So in order to actually fab chips, though, we ultimately need to produce Verilog. So we write all of our chips in Chisel. So all of those chips and all those die photos I showed a couple of slides ago, those are all written in Chisel. And then we run the Chisel compiler, runs on the JVM, to emit Verilog that then goes through all the CAD tools. So here, pretty cool, we had an undergrad who brought up a simple JVM port, the interpreted version, after quite a bit of work. And so here, this is running inside QEMU. It's probably hard to see back there. But this is taking the Chisel source for our SODOR one-stage educational cores and running that on top of QEMU on a RISC-V system, and it emits Verilog that then you can, for example, put through CAD tools. So I thought this was pretty cool. It's kind of sort of the first self-hosting RISC-V system in a way. Then continuing with RISC-V first. So next thing we did early 2016 is bump privilege spec. So the privilege spec is still evolving. This was a pretty big jump. And so we upgraded to the new privilege spec. Along with that came the first RISC-V system that you could remotely debug with GDB using QEMU's GDB server. And then we did another bump to the privilege 1.9 spec a couple of weeks ago. And hopefully we want to start upstreaming very soon as I finish my preliminary exams in mid-September. So a little bit more about RISC-V target support. So what do we support? Well, we started support back in 2014, as I showed you on the last slide, and we've been revising things as the ISA evolves itself. So we support RV64G full system emulation. User ISA support has been largely unchanged since then. It's been standardized at version 2.0. The privilege ISA is getting close to standardization, at least the machine, supervisor, and user modes. That's at 1.9. So in RISC-V 2.0 usually means standard frozen version. The nice thing, though, is that future privilege spec upgrades to QEMU will be much simpler because we kind of embedded some Spike code, at least in the non-performance critical areas, into QEMU so that it's much easier to embed, to bump things in the future. So before we did this, so back in the pre-privilege spec 1.7 days, when I had to bump it to the 1.7 spec, it took like a month to do the bring up and make sure that everything worked correctly. But then a couple of weeks ago, I did the 1.7 to 1.9 bump. I basically generated a giant diff with Spike and then applied it manually, kind of looking at what changed. This time it only took 3 days instead of a month, and so it's much cleaner to have changes go on here. Obviously, kind of once things are solid in privilege land, we want to optimize anything that's optimizable and clean things up there. Another important feature is that I/O right now is limited to host target interface devices. So host target interface, or HDiff, is kind of a relic from the days when we built test chips essentially. But right now this is enough to boot Linux. You can interact with it through a console. There's a HDiff console device. We previously had lots of other devices kind of shoehorned in before we had a real before we had a real platform specification. Right now we're working on platform standardization and adding back software support for a bunch of devices, especially things like Linux. But to look at what hardware is kind of in QEMU right now, this is a memory map that you'll see, and it's providing a reference board that's designed to match what Spike does right now. So it's giving a very simple hardware configuration. There's an HDiff-based console that's used for kind of boot messages in Linux, and you get your terminal to work with. There's also loopback software interrupt emulation, as the privilege spec requires. There's also an RTC and timers that are compliant with the privilege spec. Then a reset vector. This is ideally where you'd put like a secure boot ROM or something like that. But it's just a little bit of embedded code right now, or embedded RISC-V assembly right now. And then there's a configuration string. So there's discussion going on the mailing lists exactly about how this configuration string should look. Right now it's kind of a custom thing. I think they're moving towards having standard device tree instead of this custom configuration string. But basically this gets mapped into memory. You have your DRAM up here, and then all of your devices live down in the lower region of memory. Very quickly, what is happening to HDiff and our new debug system? So like I said, HDiff is a relic of Berkeley test chips. It's getting phased out. Basically, it was two 64-bit registers called from host and to host, and these were largely tethered systems. So you'd have an FPGA with a daughter board where the chip that we got fabbed would sit on top, and all I/O would be dealt with by stuff on the FPGA so that we didn't have to have big, complicated custom I/O IP on these test chips. So this is something that's getting phased out. It used to be able to provide things like networking, a block device, and a console, in addition to the standard VirtIO stuff that QEMU had. Now it's only for console and signaling test completion, which I'll talk about in a second. But what we want to replace this with is the RISC-V standard debug spec. So the idea is that we want to make it much easier to debug real chips once you get them. This is something that's in the process of being standardized too, and it's going to replace HDiff for sort of the debugging features that HDiff used to have. And of course, for real hardware and real software simulators and virtualization environments, they'll phase out HDiff and move to standard devices as soon as software support progresses. So kind of what happened is that all of the HDiff code in Linux got stripped out first before we had other device support, but other device support is slowly getting added back in. So I'll very quickly talk about what the software stack running inside QEMU will look like. So essentially, you have some M mode that runs your secure boot and some monitor code. So in this case, it's called BBL. It's the Berkeley bootloader. And I'll talk about exactly what that does on the next slide. Then S mode, supervisor mode, will run your OS. And the idea here is that OS always runs virtualized. So the OS interacts with the rest of the hardware through the SBI. And so you get these nice, clean interfaces. And so operating systems can run directly on hardware if you have hardware that provides an SBI and does kind of all the management elsewhere, either in hardware or other cores or something like that. But you can also do this, using a bootloader and having some monitor mode, or having, hypervisors and stuff sitting there providing the SBI. And then user mode can run applications on top of either the OS or directly on M mode if your M mode monitor supports doing that. So how this thing boots up, so you supply a binary to QEMU, which contains the bootloader. And as the bootloader's payload, you have Linux, for example. So the bootloader, Berkeley bootloader, performs machine mode management of the system, and it exposes an SBI to operating systems. So for example, when Linux wants to print to the HDiff console, it'll make an SBI call, and the M mode management code will do that for Linux, so Linux doesn't have to deal with this. The idea here is that in the long term, you can write device drivers that run in kind of outside of the OS so that you don't have to keep writing new drivers for every new OS that gets developed. Instead, OSs interact with the outside world through a standardized interface. In this case, our Linux also includes initramfs so that we don't have to deal with block devices. But we had support for that previously, and it'll get put back in very soon. So the way this thing boots up is the system boots into your hard-coded boot ROM. It'll jump into BBL. BBL will do all of this management that's listed up here. It'll initialize the supervisor execution environment that the OS expects to see. And then it'll run the kernel, in this case Linux. I'll talk a little bit about testing and debugging. So of course, when you're bringing it up, you have the usual GDB, brute force, thinking really hard type debugging. But now it passes the RISC-V standard test suite. It boots Linux too. As I showed earlier, we can run reasonably large software stacks on top. So on Python, we've done things like running image processing research stuff on top. So we developed all this stuff in QEMU, and then eventually with some fiddling, got it to run on real hardware too. We did stuff on top of the JVM, like I showed you, building things in Chisel. And so we've run reasonably large software stacks on top of QEMU on Linux. I'll talk real quick about fuzz testing against the golden standard. So we have this framework called RISC-V torture. Essentially what it does is it'll generate a random sequence of instructions based on some parameters that you supply it. So you give it some mix that you expect, some fraction of memory instructions, some fraction of floating point, atomics, whatever. It'll generate a sequence. And then since we have this golden standard implementation that is always supposed to be right, which is Spike, essentially what we do is we run our code, this generated code, on both Spike and some alternate implementation that you have, in this case QEMU. And then what happens at the end is you dump some signature, in this case just all the register state, and you compare. So if you output something that doesn't match what Spike says it should be, then you do some type of binary search to pinpoint exactly the instruction where things go wrong, and it gets reported to the person running the tests. And I made scripts to run torture on top of our version of QEMU. They're publicly available. And we've accumulated 384 hours of failure-free testing since I restarted the thing after the privileged 1.9 update. So I kind of took a bet hard-coding this number in here since I had to submit the slides a couple of days ago. But luckily, it didn't crash in the last 2 days. So the number is still correct. So ever since we did the privileged 1.9 update, we haven't had any crashes reported by torture. So things are looking good in that regard. Last thing I'll do is compare lines of code, which I know is very unfair. But ARM has 45,000, MIPS has 37,000, x86 has 30,000. RISC-V is only 5,000 at this point. So of course, this is not fair because we don't have all the legacy to deal with. But this is just to show that we have kind of reasonable amount of code, and this is with essentially no work done to kind of simplify things or clean out things that are duplicated in places. So this could probably be improved pretty decently, and that's definitely something we want to do. So last thing I'll talk about is what we have left to do and what we want to do in the future. So in terms of functionality, we definitely want to add standard device support. So this is mostly on the Linux end, thing that needs to be done on Linux. There's some stuff to be done in QEMU, like the standard platform level interrupt controller, but of course that hasn't really been standardized. There is a version of that spec'd out in the current privilege specification, though, so that's something that needs to be implemented. And of course, upstreaming. So we're planning to start upstreaming in mid-September. I submitted a very large patch, as I was advised to, just to show that the target support exists, because we were interested in potentially doing GSOC. And we got some feedback anyway on that patch. Some good stuff, for example, has already been done, like using the built-in FPU instead of our custom version of softfloat. And the torture tester also helps make sure that something like this is done right, which is pretty useful. More recently, I bumped to the 1.9 privilege spec, which took a lot less time than previously. So hopefully that's encouraging as to how stable things are getting. There are a couple of to-dos left to do, so there's a little bit more cleanup to be done, mostly I think style-wise, to get things in the right place before we upstream. Then we need to rebase to master, so we're currently using a version of QEMU from I think like December or January 2016. So we need to rebase, and then we also need to break things into small, neat patches to get things upstreaming. Luckily, I have the maintainer of Tricore helping me out here, who recently upstreamed that. And then in the future, we also want to do things like support other ISA variants, so RV32, the compressed ISA, and then also add support for things like Linux user mode. And with that, thank you, and I'll open up for questions.
All right. We only have 3 minutes left, so let me just quickly go through my 10 notes I have here. The first thing is, how does it compare to OpenRISC?
So compared to OpenRISC, there are a couple of kind of administrative things there. I think the main one was when they started working on RISC-V. So I'm not directly involved in actual development of specs or anything. When they started working on RISC-V, OpenRISC I think didn't have like 64-bit support. It wasn't exactly clear how that support would be added and stuff like that.
Okay, so it's basically the same, just a different variant.
Right. Yeah.
All right, makes sense. All the new SH4 stuff that is not SH4.
Yeah.
All right, so some pitfalls that we've seen in the ARM world. It gets complicated once you get to privileged mode on like real chips, not in emulation, because in emulation everything's easy. But if you go for real chips, then you try to model caches and you try to model like cache coherency across a cluster of clusters. It starts getting messy very quickly.
Yeah.
So give that more thought than you thought you should.
Sure.
Since that's a really good chance you will do it wrong. And in general, the basic rule of thumb is make software easier. That will eventually make your life easier as well.
Yeah.
Do you know RISU?
Sorry?
Do you know a project called RISU? R-I-S-U?
No.
It's basically a torture test for ARM.
Okay.
Well, for any platform that you like, but right now I don't think it implements anything but ARM.
Okay.
But it's the same framework. It's the same thing, just a generic framework for torture testing, and you might want to take a look. You basically just define a set of instructions and run that. It relies on Linux user emulation.
Okay.
One thing I totally have to talk about is OBS. So we basically at SUSE did an ARM64 bring up of a full Linux stack top to bottom way before there was any hardware, any working simulator that you would really want to use, because the ARM simulator is probably slower than even your slow one. All using Linux user emulation. So we basically have all the frameworks there if you want them, to just completely run everything on an x86 or even on a cluster of x86 boxes. The whole thing distributes all your builds as much as you like, and you just build a full distro. Okay. If you care. I guess you will eventually. And then virtualization is, well, that's why we're here, right?
Yeah.
KVM. When you design virtualization extensions, keep 2 major pitfalls in mind. The first is, I don't know how well you've been following the ARM development, but basically they realized after they put the first ARM version out, which had a very similar structure to you, that was a really bad idea, because you do have Linux that wants to run KVM and does not want to jump back to hypervisor mode just to be able to run to go back into a VM.
Yeah.
So the whole layer mode that is the typical university approach of doing things is not what the real world looks like.
Right.
So take that back as feedback.
Yep.
So you totally do want to make sure that you either can go really quickly between kernel and hypervisor mode, or just do something different like ARM did, where they bolted on registers to their to the hypervisor mode. But then you're running into the next issue, which is the other one, and that's nesting. Keep nesting in mind.
Okay.
Even through people, basically, I mean, we've had that 7 years ago when I first did nesting on x86, and people came along and said, oh, who needs nesting? Nobody cares. And now you basically have everybody implement nesting until it's the biggest thing ever. We had the same thing on ARM, and I'm pretty sure in 7 years we'll have the same discussion there. It will happen too. Keep nesting in mind from the beginning.
Sure. Thank you.